organizers for the kind invitation. So in this talk, I'd like to present some of our recent progress in the study of heavy quarks using transport models. So I will discuss parton interaction with the QGP at different momentum scales, including energy loss at high PT, hadronization at medium PT, and the color potential interaction at low PT. In the end, I will also discuss how parton-medium interaction depends on the size of different collision systems. As we know, heavy quarks can probe the medium properties at different energy scales. At high PT, we can study the mass and Flavour hierarchy of parton energy loss. At medium PT, we can study the hadronization process. And at low PT, we can study the thermalization process of heavy quarks and may further constrain the color potential of heavy quark medium interaction. So let me start with high PT, where the theory is clean. The evolution of the phase-space distribution of hard partons, denoted as A here, can be described by Boltzmann equation. The collision term on the right-hand side is contributed by both elastic and inelastic processes. So for elastic energy loss, the collision integral can be easily evaluated with the 2-to-2 scattering matrices. In the bracket, we have a gain term minus a loss term. The loss term can be further rewritten as the scattering rate of a single particle with a given momentum and temperature of the surrounding medium. This rate can be then implemented in Monte Carlo simulation of transport models. In our earlier LBT model, thermal partons inside the QGP were assumed massless. This has been improved in a recent work by introducing the quasi-particle masses into the model calculations. So with the thermal masses set for gluon UDS quarks, we may use the thermal relations to obtain the equation of state of the quasi-particle system. In these thermal masses, the only parameter is the strong coupling G. We parameterize it as a function of the medium temperature with 4 parameters, which can be fit to the lattice equation of state. In the end, we obtain the temperature dependencies of the coupling strength and the thermal mass, which enter our calculation of the parton medium elastic scattering rate. For inelastic energy loss, we can consider the scattering between a jet parton with a general medium. The higher twist energy loss formalism was first derived in deep inelastic scattering in large nucleus and then extended to hot nuclear matter. With the collinear expansion approximation, where we assume the average momentum transfer exchange K-perp is much smaller than the gluon transverse momentum L-perp, which is further much smaller than the jet energy scale Q. Then we can obtain such medium-induced gluon spectra. The medium information is all absorbed in this jet quenching parameter Q hat, which characterizes the transverse momentum broadening of the jet parton per unit time. Using this spectra, we may implement Monte Carlo simulation of gluon emission from hard partons. Using this model setup, we show in a recent study that the clean perturbative framework is sufficient for describing the Flavour hierarchy of jet quenching at high PT. First of all, we note that the next leading order production of heavy quarks is important, which was usually neglected in theory calculations. This NLO production can be mimicked by the gluon splitting process in Pythia. We see its contribution increases with the collision energy, as well as the heavy Flavour jet PT, as shown by the green part in the plot. On the right, we show the charged hadron versus d meson spectra in proton-proton collisions within this NLO production plus fragmentation framework. In each figure, we compare contributions from initial gluon and quarks. We see that the gluon fragmentation plays different roles in charged hadron production and d meson production. It dominates charged hadron production up to only about 50 GeV. Beyond that, quark contribution dominates. However, gluon fragmentation contributes to over 40% d meson production up to 100 GeV. For heavy ion collisions, we couple this NLO framework with our Boltzmann transport model inside a hydrodynamic medium for QGP. Here we show the nuclear modification factors left for charged hadrons and right for d mesons. again compared between contributions from initial gluons and quarks. Comparing between green and blue curves, we see the gluon-initiated light hadron and the d-meson RAA is smaller than the quark-initiated RAA shown by the blue curve, which is consistent with our expectation of the Flavour hierarchy of parton energy loss. On the other hand, although the RAA from charm quark to d-meson is larger than the RAA from the light quark to charged hadron, the RAA from gluon to d-meson is actually smaller than the RAA from gluon to charged hadron due to different fragmentation function. After combining all contributions, we see that the charged hadron and d-meson share similar RAA, starting from 8 GeV. We can further confirm our findings by implementing the same calculation for B mesons because B quark has even larger mass. Here we see this clean perturbative calculation provides a simultaneous description of charged hadron, direct D meson, B meson, and B decay D meson, starting from 8 GeV. We also predict the B meson has a sizable larger RAA than charged hadron and D meson when PT is not very high, but the RAAs are all become consistent starting from about 40 GeV. We expect the future precision measurement may help confirm such momentum dependence of the Flavour hierarchy of jet quenching. Now let me move down in the momentum scale. At medium to low PT, we know the non-perturbative hadronization process becomes important. For jets, it has been shown that the effects of hadronization is as large as the effects of introducing the next to leading order correction in describing the cone size dependence of the jet cross-section. A recent study also shows that for medium PT hadrons, including the recombination between jet partons and medium thermal partons is crucial for the simultaneous description of RAA and V2. And we know that there are two major hadronization mechanisms. High momentum partons tend to fragment directly into hadrons. We can use a well-tuned fragmentation function to calculate the hadron spectra or use PCR to simulate this process. On the other hand, it is more probable for low momentum partons to combine with thermal partons from the medium to form new hadrons. This is known as the coalescence or recombination mechanism. So in our work, we developed the instantaneous coalescence model, which is based on the sudden approximation in quantum mechanics. As the medium temperature drops across Tc, we assume the quark-gluon degrees of freedom suddenly changes to the hadron degree of freedom. Therefore, the coalescence probability is given by the wave function overlap between the free parton state and the hadron bound state. Therefore, the model naturally encodes the information of the macroscopic hadron structures. The final hadron spectra from this coalescence process is then given by the integral of the parton distribution function times the this coalescence probability times a delta function that conserves the three momentum. For parton distribution function, we assume thermal distribution of light quarks in the local rest frame of the expanding QGP. For heavy quarks, their distribution can be obtained from the transport simulations as discussed earlier. Recently, this coalescence model has been improved in two aspects. First, in addition to S wave, a complete set of P wave states have also been incorporated. This naturally enhances the total coalescence probability and is able to include nearly all charmed hadron states in the particle data group. Including P-wave contribution allows us to normalize the coalescence probability for zero momentum charm quark with a proper in-medium hadron size. An earlier defect of this coalescence model is it only respects free momentum conservation, but violates the energy conservation. We solve this problem by first coalescing to the off-shell excited states and then decaying to on-shell ground states. This guarantees the boost invariance as well as the thermal limit of the produced hadrons. For example, here we start with thermal charm quarks and also thermal light quarks inside a static medium with 160 MeV temperature. Then we find the produced D meson via coalescence denoted by the red crosses here, also follow the thermal distribution with a temperature parameter as 160 MeV. By combining the PCF fragmentation and this coalescence process, we study the charm hadron chemistry in heavy ion collisions. The upper figure shows the PT integrated lambda C over D0 ratio, where we study the effect of the QGP flow on the baryon to meson ratio in hadron formation. We see a stronger QGP flow boost on heavier hadrons, which increases this lambda C over D0 ratio as the participant number increases. In the lower left figure, we show the PT differentiated lambda C over D0 ratio. We see that this coalescence significantly enhances this ratio compared to PCF fragmentation. And we also see that a larger value of this ratio in more central collision due to the stronger QGP flow. The lower right panel is the DS over D0 ratio. It is also enhanced by coalescence due to both the stringiness enhancement in QGP and also the larger DS mass than D0. If the QGP flow can enhance these ratios, one should expect larger values at the LHC than at RHIC. However, this is not the case as shown by the data. To understand this difference, we first assume the charm quarks at RHIC and LHC share the same spectrum. Of course, this is just an assumption. With this assumption, we see that the lambda C over D0 ratio is indeed larger at LHC as shown by the maroon line than at RHIC as shown by the blue line due to the stronger flow at LHC. However, after taking into account different spectra at RHIC and LHC, the maroon line at LHC will drop to the realistic red line at LHC, which is also smaller than the ratio at RHIC due to different charm quark spectra. On the right, we have similar prediction on the DS over D0 ratio at RHIC versus LHC, but the difference is much smaller than lambda C over D0. We can further test our calculations with the BS over B plus ratio. Beauty quarks are much heavier than charm quarks and thus can place more constraints on the mass or velocity dependence of hadronization models. Here we assume the same diffusion coefficient between charm and beauty quarks. And as shown by the green curves taken from the CMS figure, our model is able to predict the BS over B0, BS 0 over B plus ratio. As suggested by the organizer, we also did the homework from this workshop to check the hadronization effect. So we can define the HAA as the ratio between the hadron spectra and the charm quark spectra to see the hadronization effect. We see the coalescence enhances this ratio at low to medium PT. The enhancement is stronger for lambda C over D than for lambda C spectra than for the D meson spectra. We have also checked the V2 effects. So in task 2, where C quark V2 is 0, we expect to see charm hadron from fragmentation also have 0 V2 as shown by the black curves. However, after coalescence is introduced, a non-zero V2 is observed as shown by the red curves. In task 4, where C quark is V2 is already finite, charm hadron from fragmentation already show V2 as shown by the green curves. But this V2 is further enhanced when coalescence is introduced as shown by the blue curves. We also see this enhancement from coalescence is stronger for lambda C than for D mesons. Now let me move further down to low PT. At low PT, we know that the dead cone effect suppresses the radiative energy loss of heavy quarks. Therefore, the heavy quark motion is dominated by diffusion processes, which can be quantified by the momentum space diffusion coefficient kappa or the spatial diffusion coefficient ds. However, we see that the NLO result of this kappa calculation is larger than the leading order result by a factor of 5 when alpha s is around 0.2 to 0.3. This indicates the failure of the perturbative method for low momentum heavy quarks. So recently, we tried to introduce this non-perturbative effect into our transport calculation. Instead of scattering between quasi-particles perturbatively, we let heavy quarks scatter with general potential. We follow pioneer work to parameterize this interaction parameter with two parts, the Yukawa term and the string term, in which the MD and MS are the screening masses, alpha S and sigma are the coupling strengths of the two terms. The corresponding parameters can be fixed to the lattice potential from pioneer works. After Fourier transformation, we have the color potential in the space of the exchanged momentum. We can then replace the propagator in perturbative calculation with these interaction potentials for scattering amplitude and evaluate the scattering rate between heavy quarks and the QGP. The first term will reproduce our original perturbative calculation result, while the second term will introduce the non-perturbative effect. Here are our numerical results for the D meson at RHIC, left for RIA and right for V2. In the plots, blue curves are contribution from Yukawa term, and green are from the string term, and red are their combination. We see from both RIA and V2 that at high PT, the Yukawa interaction dominates the heavy quark medium interaction. On the other hand, at low to intermediate PT, the string interaction dominates. We also note in our calculation that after introducing the string term, there will be a stronger contribution from the QGP properties at a later evolution stage, since the string term is larger near TC. These are our results at the RHIC energy, left for RIA and right for V2. Compared to previous results at RHIC, we see effects of the string interaction appear even more important for understanding the PT regime studied at RHIC. Without it, we cannot get sufficient suppression of D mesons. We see that the combination of the short-range Yukawa and the long-range string interactions provide a reasonable description of the D meson RIA and V2. So in the end, let me try to move on to use the heavy quark transport model to study the medium property at with different sizes. There was a puzzle raised in the P-led collisions where we observed pretty large V2 of D mesons up to 8 GeV, but almost no suppression. No suppression would imply that this V2 may not come from the QGP effects. In a recent work, it has been shown that the initial state effect can successfully explain the large V2 of both open and open charmed meson and charmonium in P-led collisions. Now the question is how to separate initial state effect and QGP effect. We expect a system size scan of jet quenching can help bridge the large and small systems and may tell us how the QGP effects become weaker and in the end disappear as the system size shrinks. First, we investigate how the hadron RIA depends on the system size, left for charged hadron and right for D meson. As we move from lead to xenon, argon, and in the end to oxygen collisions, we can clearly see a rise of the hadron RIA, indicating a clear hierarchy of parton energy loss with respect to the system size. Interestingly, we still expect to see significant hadron RIA in small oxygen system, indicating the existence of QGP at this size scale. Here we present the PT integrated hadron RIA as a function of the participant number. Results from different collision systems now appear lining up on the same curve. This confirms the scaling of the hadron RIA with the system size and further indicates the observed P-led close to 1 is mainly due to the small size of the medium produced in proton nucleus collisions. We also investigate how the hadron V2 depends on the collision system. We notice V2 is determined not only by the amount of energy loss, but also by the geometric symmetry of the medium. In the left figure, we see that when the geometric symmetry or the collision centrality is fixed. Larger collision systems usually lead to stronger energy loss, therefore larger V2 of d mesons. In the right figure, we see that when the participant number of the system is fixed, V2 increases from oxygen to argon to xenon and to lead collision due to the increasing geometric anisotropy. In order to separate the energy loss and the geometric effects on V2, we may rescale the heavy meson V2 by the bulk medium epsilon 2. So here left for D meson and right for B meson. This is what is left for the pure energy loss effect. We see that this V2 over epsilon 2 value from different collision systems line up around the same curve, indicating the scaling of this observable with the system size. What we present here is the pure QGP effect. When experimental data become available in the future, we may search for the point when such scaling breaks. That will indicate the system size where the initial state effect overwhelms the QGP effect. Okay, to summarize, in this talk, I have discussed the parton-medium interaction at different PT and also in different collision systems. We see that the QCD calculation is sufficient to describe the flavor hierarchy of jet quenching above HGeV. Coalescence plus fragmentation hadronization is crucial for understanding hadron chemistry at medium PT, and color potential interaction significantly improves the model calculation at low PT. In the end, we see that we expect that the scaling behaviors of hadron RAA and V2 across different collision systems may help distinguish initial state and QGP effect at different system size. Thank you.
Thank you very much, Shanshan, for a very rich talk. There a question on where?
For the last point, you show predictions, expectations for different collision systems. I was wondering whether one can try to do the same in peripheral lead-lead collisions. So looking at the evolution with centrality of RAA and V2 together. And do you expect this to provide useful information with, for instance, precise measurements from round 3?
You mean the centrality dependence of these observables, right?
Yes.
Actually, that's already included in this calculation. So yeah, I think in this plot, when we you see that so each curve corresponds to each collision system, and different points correspond to different participant numbers. So it's already included.
Okay. And so it gives you more. So the points are more or less following on the same curves, right?
Yes. We are trying to search for certain scaling behavior with respect to the system size.
Okay, I see. Okay.
There was another question by Elena.
Hi, Shanshan. Thank you for the talk. I have a question concerning the treatment of inelastic energy loss. On slide 6, you showed the formulas for your height with collinear expansion, which you use. And here I have a question. How do you compute Q hat? And if your new description of the partons in terms of quasi-particles also entering consideration of inelastic energy loss?
Oh, okay, thank you. So the Q hat here is from the 222 scattering. So similar to the 223 process can be factorized into a 222 scattering plus a 122. So in our calculation, this Q hat is from the 222 elastic scattering, the momentum broadening. So in quasi-particle model, we introduce the mass and still calculate this Q hat using the elastic process.
Just because we are here, Shanshan, but when you do this, you don't include the fact that the gluon that you radiate is massive, right?
No.
It's
The
still
gluon,
like...
the radiated gluon is still considered massless. the thermal gluon inside the medium massive.
Okay. But you plan to do also that work to try what happens if you put the mass on the gluon? It's not easy. But...
We really want to try that, but that would be a challenge to start from beginning of this theory calculation first. But I think it's a very important task to do in the future.
Okay. There was Francesco Prino that raised his hand.
Yeah, hello, can you hear me?
Yes.
Yes, no, I have a short question about what you have shown in slide 20. So the REA and V2 with the UCAV and the string potential. Yeah, the question is simple. For the hadronization, did you use in this prediction what you have shown a few slides before this? So the improved instantaneous coalescence with energy conservation and P waves states?
Yes, so in these two plots, the exact the same hadronization that I show in this talk is used for these two plots.
Okay, thank you.
Okay, Paul.
Yeah, thank you, Shanshan, for this very nice talk. I have two little questions. First, how does this new energy loss mechanism affect the DS versus T curve and the comparison with the lattice? I mean, does it move it quite a bit or not? And then the second question is, those system centrality and synthesized dependence have also been studied recently by Roland Katz and Jackie Norola-Hausler and collaborators. So do you find some difference with respect to the studies, or do you reach the same conclusions?
I think for the same observable that we study, they are consistent. But here we just extend their study and trying to find a certain scaling behavior that different systems can follow together, and use maybe a little more sophisticated model calculation. So, but qualitatively, all the conclusions are consistent. But for your first question, sorry, I didn't follow. You say the effect of what?
Well, we all put a energy loss model. Then basically we have this DS as a function of temperature, you know, this kind of famous plot where you accumulate the different models. So now you have different models where you input the string, okay, on the top of it. So in principle, you have a new DS as a function of the temperature. This diffusion.
I see your point. Okay, thank you for your question. So it's like this. The short answer is, in the end, we don't see much effect on the final ds over d. So the reason is, in earlier calculation, when we use the pure perturbative calculation, we need to tune the k factor to describe data. And the point here is that we try to remove the k factor and try to build up like a more sophisticated model to describe this interaction. But in the end, when they describe data, the extracted ds seems very similar.
Very good. And Shan, just okay. I mean, your talk was very rich or many things, but about coalescence, you essentially enforce a kind of confinement, changing the radius of the meson. This somehow can seem that is a bit arbitrary, but I ask if when you do this, you do in a coherent way also for lambda c, or you just change the RD, I mean, because this may affect a lot the ratio. How it is done?
Let me confirm. Is your question is this parameter different for D and lambda C?
Yes, yes. You do that.
Here, okay. So here we try the minimal model. We use the same. Okay. It's not the R that's the parameter. You know, in the coalescence, it's the omega. The frequency is the parameter. We assume the same frequency. And okay, then
so you change the frequency.
From the frequency, yes.
So that change affects all the radii, also of the other, also of the lambda c, for example, right?
Yes, yes.
Okay, okay. Thank you. If there are no other questions, let's thank again Shanshan.